Hello, my name is Michael Martinez, and I'm here to present my journal paper critical review for an article called Wavelet Transform-Based Speech Enhancement. In this article, we're going to be considering the author's approach to enhancing speech for a particular case with noise for cell phones, and the approach that the authors decided to take in enhancing the speech. For the authors, there was a problem mentioned by the authors is that when it comes to cell phone usage in cars and moving vehicles, there is a specific type of noise that is non-Gaussian that results. So the authors claimed that there was insufficient research regarding this type of noise, so this was their interest. So they decided to go ahead and apply different types of filters or to compare with their new approach, which was using a fast wavelet transform and a Wiener filter for a wavelet domain. So that's their approach, but they decided to compare that with conventional fast Fourier transform with Wiener filters or thresholding with wavelet coefficient values. So those are the conventional ways that they went ahead and compared with. So the usage of the fast wavelet transform was used in order to get the wavelet coefficients from a noisy signal. So as you can see here in this diagram, a noisy signal is produced, it's entered into the fast wavelet transform. And as you can also see, there are 5 subbands that result as well. And finally, we have our enhanced speech, but this is just a conventional diagram without the actual input from the Wiener filter. So this is just to show the process of decomposition and reconstruction from the wavelets. This right here is the conventional Wiener filter block diagram, and in here we would normally have a signal input with some noise. And typically the Wiener filter will give us our input signal, a desired input signal. So in typical filters you would have an output that is random, since your input is also random, even though it may be a function of a particular variable. Typically they're random still, it's got a randomness to it. So the output will also be random. But the Wiener filter, it works by minimizing that randomness. So this is the basis of what the authors applied in their method for speech enhancement. So as I had said earlier, the Wiener filter minimizes that error between the desired signal and what you actually come up with from the filtering process. So what they do is minimize the mean square error of the signal, the input signal, the desired input minus the actual output that comes out, the actual input that comes out. So when they minimize that, what they do is they take the mean square error and they go ahead and differentiate it with respect to the filter coefficients. And when you set them to equal to 0, you can find an equation, which is this equation right here, that will give you conditions. So in this term, we'll have the autocorrelation functions, which is the RSS of the signal itself, or the speech signal really. And over here, multiplying against our coefficients that we're trying to find for the Wiener filter, we have our autocorrelation functions for the speech and noise together. So using these coefficients, calculating these coefficients, we can find the filter coefficients that we want for the Wiener filter. So what you can do also is that you can take the relationship between the autocorrelation functions and the power spectrum density function. And when you take the fast Fourier transform, you can find the gain, but essentially the transfer function of this equation. So you can do that and you'll have it in the frequency domain. So that's a conventional transfer function for the Wiener filter, but with frequency domain. The steps that the authors decided to take was assume some properties of the wavelet transform. So there was no mathematically rigorous derivation to how they approached this result here, which is basically they replaced the frequency with the scale values of the wavelet transform. And they decided to say that this was the transfer function for this. This is the transfer function of the essentially the Wiener equation in terms of the wavelet domain instead of the frequency domain, as we see here. So that was their approach. They decided to take that kind of approach, which we'll discuss later about whether or not that was a right choice or a wrong choice. So using that transfer function in the scale domain, so what they were able to do was calculate these gain values, which is called the Wiener gain values, and that's our Ki here. And you can calculate the gain for a certain signal, S, I, and a certain noise at that signal as well. So you can calculate these coefficients, these Wiener gain values. And as I said, this came from the transfer function. So the transfer function is the gain of that system. And using those individual gains, we can calculate the coefficients that we'll be multiplying the wavelets by, essentially multiplying each of those gain coefficients, gain values with the coefficients that you would normally have for a noisy signal for a wavelet transform. So you doing that, you would have the coefficients, now the new coefficients for your wavelet transforms, and they will be for the denoise signal. So as results for the experiment that the authors used was actually subjective. So they decided to go ahead and play it by ears, see what sounded better, whether or not their way of enhancing the speech was better from thresholding of the wavelet coefficients, which is also called the Donohue method, as they mentioned, or using a fast Fourier transform with the Wiener filter as well. They decided to go ahead and play these out by ear, which we'll be discussing whether or not that was a good idea. So from their results, they showed that with that subjective test, that theirs was better. They got better results. They were able to hear more better. There was a better speech enhancement for that situation of a person on the cell phone in a moving car with that noise. And that noise input also, as I should mention before we go ahead, that simulated noise was non-Gaussian. So it wasn't nice and flat. It was actually had a non-homogeneous form to it along in its spectrum, in its spectral graph. So the pros and cons. So the paper showed the different techniques that were involved in speech enhancement. So that was also that was a pro. So that's good that you be able to compare your results with different results to see whether or not your results are better or not. And they also simulated the non-Gaussian noise to demonstrate capability of that filter. So a lot of this was actually a problem that a lot of the other filters had when they tried applying to this situation, was they had to kind of change out the conventional methods that they use to speech enhancement with the fast Fourier transform and Wiener filter and the thresholding of the waveform coefficients. So that was a pro. Cons, the fact that the tests were subjective, they could have easily just measured the signal to noise ratio afterwards to get an objective value for their tests, and for sure can tell whether or not their speech was enhanced or not. So there was some bias in there. There probably was bias since this was a subjective test. And the lack of mathematical rigor. So from when they were assuming the form of the Wiener transfer function, the transfer function of the Wiener filter, they decided to go ahead and just simply replace frequency with wavelet coefficient scale. So that was also that was a big problem that I saw with the report. Thank you very much.